Okay, so let's take a look at this next one. So it says a student dissolves 1.42 grams of sodium hydroxide in 250 milliliters of solution. Calculate the resulting hydronium and hydroxide concentrations and justify this as basic. So of course we know this is going to be basic. It's a strong base. So we have to determine the concentration first. So we have 1.42 grams in I'm going to convert this to liters since we're going to need moles per liter. So we have 0.25 liters times for every 1 mole. The molar mass of NaOH is approximately 40. It's pretty much, it's like 40.00 something, but it's pretty much bang on 40. So for moles per liter here, we're going to get 0.142 moles per liter. And this is the concentration of sodium hydroxide. But again, the same reasoning that we saw with the first example we went through, this is also equal to the concentration of hydroxide since it's a 1-to-1 ratio and it's a strong base, right? So we can just assume looking at mole ratios. So then we have our relationship between Kw, hydronium, and hydroxide. We have our Kw and we have our hydroxide value. So Kw, of course, is still our 1.0 times 10 to the negative 14. So the hydronium concentration you calculate here ends up being 7.04 times 10 to the negative 14. And we do need 3 significant digits. Remember, this decimal point that's here is giving that last 0 significance. So of course, this proves that our hydroxide concentration is definitely more so than hydronium. Okay, so this next part is looking at, well, what happens if you have a strong acid and a strong base that are being mixed? So when you have a strong acid and a strong base coming together, really, right, the hydrogen, which essentially becomes hydronium in water, will neutralize the hydroxide that's coming from our strong base. So what ends up happening is if you were to add, for example, equivalent amounts, you would end up with a neutral solution, right? So let's just say, for example, let's do NaOH and HCl. Okay, and we're only dealing with strong acids and bases in this section, okay? So let's say we had 5 moles worth of NaOH, and I'm only going to refer to moles here because if I did moles per liter, for us to determine the products, we would have to consider the dilution effect, right? But by looking at moles, I'm just straight up looking at like essentially the number of particles. So if I had 5 moles of NaOH and 5 moles of HCl, like equivalent particles, that means that these would essentially fully react and all of that would become product, right? I'd have like 5 moles of this and 5 moles of this, right? So this would then be a neutral solution because there was no remaining hydroxide or hydrogen left over from our acid and base, right? So if you have equal amounts of strong acids and strong bases that are mixing, you're going to have a neutral solution. But you may not always have equivalent amounts. So let's say instead of having, let's do 5 moles of NaOH, but I'm going to only add 2 moles worth of hydrochloric acid. So what ends up happening is 2 moles out of the 5 moles of NaOH would be used to neutralize this out. Sorry, sound on. So basically, 2 out of the 5 moles would be used to neutralize this HCl. But because now I no longer have all of my reactants being completely used up, I'm going to have leftover hydroxide coming from my NaOH that's been remained unreacted. So this would then result in a basic solution. The same thing would happen, obviously, vice versa, if you were to have excess HCl and you have more HCl than you had NaOH, so there would be excess left over. Your solution would then become acidic. So only when you have equivalent amounts neutralizing one another do you end up having something that is perfectly neutral after you mix solutions of strong acids and bases. So we're going to take a look at 3 practice problems that are going to be essentially doing what we're saying here, obviously with some numerical data. So we're going to calculate the final hydronium and hydroxide concentrations in a solution formed when, so now we're dealing with volumes, right? We have 150 mils of a 1.5 liter mole per liter nitric acid and 250 mils of 0.80 mole per liter KOH. So the first thing we need to do is we need to figure out what is the concentration after dilution. Okay, so I didn't really deal with that here because this is just getting the concept down. But when you're asked to solve for the final concentration, you have to first get the concentration upon mixing. So we're going to have to do our C1, V1, C2, V2 again. So just to clarify, because I'm going to simplify this, it's really C1, V1 over V2, right? So let's do our nitric acid first. So this is going to be 1.5 moles per liter times 150 mils over the total volume afterwards is 400 mils. And we would do the same thing with KOH. I'm just going to set this up here. So this is going to be 0.80 moles per liter, 250 mils over 400 mils. So we have 0.5625 moles per liter, right? Don't round anything as of yet. And this ends up being just 0.5 moles per liter. So what does this mean? This is the concentration of hydronium, right? Because it's a 1-to-1 ratio. Remember, for every 1 nitric acid, we're going to get hydronium. And this is equivalent to our hydroxide for the same reasoning. These two numbers are not equal. So what that means is you are going to have, just by looking at this, I can see I'm going to have excess nitric acid or hydronium left over. So to figure out how much is left over, you literally subtract it. So 0.5625 moles per liter minus 0.5. So my leftover remaining hydronium is going to be 0.0625 moles per liter. Okay, we're probably wondering now, well, the question asked us to solve for hydronium and hydroxide. So you're probably thinking, but didn't the hydroxide all get neutralized? But we still have this in an aqueous solution. So what that means is because we know our hydronium concentration of what's remaining, we can use the Kw expression to determine what is the hydroxide concentration coming from essentially whatever happened to be coming from just the water. So the KOH, hydronium, has been neutralized, but we still have hydroxide. Hydroxide and hydronium will always be present in some amounts anytime you have water present. It also doesn't say to assume 25 degrees, but unless you're told otherwise, you are to assume 25 degrees. So this is 1.0 times 10 to the negative 14 is equal to 0.0625 and then x. So our x ends up being for hydroxide 1.6 times 10 to the negative 13 moles per liter. And I just realized we needed hydronium to be, so our final hydronium concentration just for sig figs, we need 2. So it would be 6.2 times 10 to the negative 2 moles per liter. So remember that if you're rounding, when there's a 5, if you look next door, if there's numbers there, there might have been numbers. No, there were not numbers there. But perhaps if I did not round here, there would have been numbers. This is why it is important not to round. Let me just quickly do that again. I can't remember if that was it. Nope, that was the straight up number. Ah, so it is what it is. So we would keep that as a 2. There's our final answer. Okay, so again, obviously pause the video wherever you would like to give these a try on your own. Okay, so calculate the mass of solid NaOH that must be added to 500 mils of 0.2 hydroidoic acid to result in the solution of, assume no volume change on the addition of the solid NaOH, which is good. We don't have to deal, so there's no dilution, no C1V1, C2, V2 business going on. So essentially, we're trying to kind of work our way backwards. So we have the HI concentration. So we have 0.20 moles per liter, and we have 500 mils, right? So our NaOH. So we want to be left with a resultant 0.12 moles per liter. So you have to think that essentially there should be 0.12 moles per liter of HI remaining after NaOH was added. So really what that means is we need 0.08 moles per liter? Yeah, moles per liter of NaOH, right? So let's do the math, right? So if we need a remaining H3O, it would be 0.20 minus 0.08. This would give us the 0.12 mole per liter that we are looking for, right? That's how much has to be remaining. I'm hoping that makes sense, right? So we want, this is initially HI after the goal was 0.12 mole per liter. So you essentially want to neutralize out 0.08 moles per liter worth. So then, now that we know this, we can determine the mass, because if it's 0.08 moles, I'll write it down full so we can see this, and it's going into a 0.5 liter solution, and we multiply with the molar mass. Again, NaOH is pretty much 40. We end up getting a value here of, to 2 significant digits, 1.6 grams. So instead of them telling us how much we're adding to each other, they're giving us how much should be resultant afterwards. Okay, so let's try and squeeze in this last one here before my time runs out on this part. So calculate the resulting, it's gonna be a long one, never mind. Calculate the resulting concentrations when we have this added to this. So this is actually very similar to the first one. So we have, you have to do the dilution equation. So dilution equation after mixing for HBr ends up being, when you calculate it using C1V1, C2V2, HCl after mixing. Now we're going to have to continue this because there's something sneaky going on in this question. I probably shouldn't be recording this video like so late. I'm making like silly comments, but okay, stay tuned for the next part, because what you should have noticed is they're both acids. There's no neutralization going on. Okay, I'll see you in the next part.